I'm going to use some graphs to derive some equations. So we're going to start off with the simplest possible graph, a graph of position versus time when the object has no acceleration. So whatever speed it has is going to keep that for the whole time. And in this case, a position versus time graph like that, here's my position, which we'll measure in meters. Here's time in seconds. And like we saw in an earlier video, if I have a constant speed, I'm going to have a straight line position graph because my motion map would show that I basically cover the same amount of distance every second. So if I wanted to take the slope of that thing, that would be equal to your rise over your run, or your change in y over your change in x. But this graph doesn't have an x-axis and a y-axis. This graph actually has a position axis and a time axis. So slope equals change in position over change in time. And at this point, that might not mean much. So let's kind of flesh it out here for a second. We measure positions in meters, and we measure times in seconds. So you might recognize this, a meter per second or a meter in a second, as a unit of speed. So what we can say is that the slope is the speed, and that's equal to change in position over change in time. Basically, in some graphs, slopes are so important that we name them. In this case, we gave this slope a name. We called it speed or velocity. So let's flesh this out a little bit further. We know that speed, we're going to call that v, is equal to a change in position. So we could have change in position in the x direction or the y direction. So let's just say it's like change in x over change in t. And I'm going to rearrange this, bring my time to the other side, and say change in x equals speed times change in time. Now, changes in time's always changing. So you'll notice that we get pretty loose about the change in time part, and we just call it time. But a change in x is going to be our final position minus our initial position, and that's equal to v times t. Or I could rearrange that further and say my final position is equal to my beginning position plus my speed times my time. And this is an important equation to have on hand. You're going to use it a lot. All right, now let's check out something. Here's my AP physics equation sheet. And if you look, this equation doesn't really exist in here. So what's going on? I gave you an equation that's not on the AP physics equation sheet. AP considers this too simple. They expect you to have it memorized. So you should be able to point out that if you change your position, that's equal to a speed times a time. That's just, they expect you to know that. Now, another thing that's important about graphs is the area underneath them. Okay, so if I took a look at this area, I'm going to divide it into a rectangle and a triangle. And I'm interested in what this area can tell me. Because sometimes in graphs, an area is really important, and we're going to name some of them. So let's check out the area here. So my area under my curve here is equal to this rectangle. And a rectangle has a length or an area of length times width. Let's change that to blue here, length times width. And my triangle has a length of 1/2 base times height. So if we come down here, my length times my width, well, my length, let's say, is my position. So that would be a position, and my width would be a time. And if I multiply positions times time, I get a meter times a second, which hopefully you recognize has no meaning. Like you've probably never seen it before. Physicists don't use it. A meter second, I can't think of a time when it's useful. So what about the triangle part? It's 1/2 my base is time, and my height is position. So I wind up getting a second meter, also useless. So in this case, there is an area under that curve. You could solve for it, but we don't use it. Okay. Now, why did I do that? Because we're going to see some graphs where that area is actually important. And I'll give a plug for calculus here. What I'm doing is a cheesy way to find derivatives, because derivatives are slopes, effectively, and integrals. Integrals are the areas under a curve. So I'm laying down the foundation of calculus by showing you some physics problems. Okay, let's keep moving on. So there is an equation that's pretty important. It's your final velocity equals your initial velocity plus your acceleration times time. And we want to find out, where does that equation come from? So again, we're going to take a look at the slope of this equation, and we're going to take a look at the area underneath it. Okay, so let's start with the area part. Let's say I take a look at this area right here. It traces out a rectangle, right? And the area of a rectangle is your length times your width. So my area equals my length times my width. But my length is my time. Or let's do it this way. My length is going to be my acceleration, A, and my width is going to be my time, T. So this area is an acceleration times a time. Now, accelerations are measured in meters per second, and times are measured in seconds. So I can cancel out my seconds, and I'm left with a meter per second, which you should recognize is the unit for speed. So the area underneath that curve is equal to a speed. Now, the weird thing is, which speed? Is it my beginning speed? Is it my ending speed? And actually, the graph doesn't tell you. We don't know whether you started at 1,000,000 meters per second and you're increasing that, or whether you started at 0. So what this graph actually tells you is only your change in your speed. Okay, so change in speed is equal to acceleration times time. So I'm going to rewrite this to make it a little bit clearer. Change in speed is acceleration times time. And my change in speed is my final speed minus my beginning speed, is that. And I'll pull my beginning speed to the other side and say V final equals V initial plus acceleration times time. Another super important equation that you need to hold on to. Let's check our AP Physics equations again. Does it exist? And the answer is yes, right here. But that's not the equation that I wrote. I wrote VF equals VI. This is VX equals VX0. What's going on there? So they're trying to point out that this V is actually a vector. And the X says that you are moving in the X direction. They could have written it as Vy equals Vy0 plus AT. Then they'd be telling you that you're moving vertically in the Y direction. I didn't bother to put a direction down here because I'm working in scalars. The other thing that's weird is this 0. That 0 tells you it is the first speed, the beginning speed. So I tend to use F's and I's for final and initial. AP doesn't. They just say of speed, any speed, is equal to your beginning speed, the speed when time was 0. So I just need you to know that when you're looking at this equation sheet, you can say, oh yeah, I remember what this is. Now you notice that the A also has an X, and that's because it's a vector, and they need to tell you what direction that acceleration is in. Okay, let's take a look at the slope here for a second. So I'm going to change colors. My slope of this graph is equal to my change in Y over change in X, but I don't have a change in y and I don't have a change in x. I have a change in acceleration over change in time. We know that acceleration has a unit of a meter per second, and time is in seconds. So this would be a meter per second. No. It actually has a meaning. If you're an engineer, I believe this thing is called a jerk, but we don't use it. In this case, the slope of this graph is going to be meaningless to us. People, like I said before, people do use it, but not in this class. So in this case, only the area was important to us. Okay, let's take a look at this next graph. So I've got a speed graph, and it's clear that my speed is increasing. It's going from 20 to 100 meters per second over a period of 8 seconds. Oh, actually, yeah, I said that right. So let's start out with the area underneath this curve again. And I'm going to break it into two parts. I've got a rectangular part here, and I've got a triangular part here. So this area right here is equal to a length times a width. And the triangular part up here is 1/2 base times height. So, sorry about that. So let's start off with the rectangular piece. My area is going to be my length, which I'm going to call my time. And my width is going to be my speed. Now, which speed is that? It's actually going to be my beginning speed because my graph starts right here. That's my first speed. Now, since we're at it, I'm stopping right here at 8 seconds. So at 8 seconds, this 100 meters per second is my final speed because that's where I'm ending the problem. Okay, so my area of the rectangular part is my time times my initial speed. And I've got the area of the triangular part, which is 1/2. My base is going to be time. And my height, you would think, is V final. But be careful because actually the height of the triangle here starts here and goes to here. So it's the difference between my beginning speed and my ending speed. And in physics, we always subtract end minus beginning. So I've got this crazy equation, and I'm going to rearrange it because physicists never put time first in an equation for some reason. So my area is going to be VI times T, and I'm going to distribute all this mess. So it's going to be 1/2 VFT plus a negative 1/2 VIT. Okay, wait a minute. I have some like terms. I have a positive VIT and a negative 1/2 VIT. So if I add those together, I will get 1/2 VIT plus 1/2 VFT. Get rid of that. And I have some more like terms. I have a half here and I have a T. So I can pull that out and say, well, look, VI plus VF times T. And I've arrived at my equation right here. Kind of. How do I know that it's a position? And I know it's a position because speeds have a unit of a meter per second, and times have a unit of a second, and half doesn't have a unit. So the seconds will cancel out, and I'm left with meters, and meters measure position. But my equation up here says change in position. Why is that? Well, I actually don't know where I started, right? I could have started at 0 or I could have started at 20. And all this tells me is how much I've increased my position. So this is going to be my change in position. So now I'm at my equation here. Change in position equals VI plus VF, half of that times T. Now, if we look on the equation sheet, It's not there. Okay, why isn't it there? Again, AP Physics thinks that this equation is too easy and they pretty much ignore it. Okay, so they don't care. Now, how do I get from this equation to change in position equals V average times T? Well, if you take two things and add them together, if I said you got a 50 on a quiz and you got a 100 on a quiz, what's your average quiz grade? You would add your quizzes together and divide by 2. So here I've added two speeds together and multiplied by a half. That's the same thing as dividing by 2. So this chunk right here finds your average speed. Half of the total of your speeds is your average. So your change in position is equal to your average speed times your time, which the reason it's so obvious is because we already know that position is equal to speed times time. So your average speed times time is still a position. They don't want you to do too much with it. Okay. Before we leave this page, I want to point out one more thing. If I rearrange this equation up here, so let's bring it back down. VF equals VI plus AT. Bring my VI to the other side. VF minus VI equals AT. This is going to be my change in speed divided by time is equal to an acceleration. Okay. That I'm checking out my physics equation sheet, also not in there because they just expect you to know that. Accelerations are change in speeds over change in time. But we're going to need this equation on the very next thing that I do. So let's take a look at that. We've got one last equation we need to figure out. So I'm going to take this thing and we're going to find our area one more time. Okay, it's the same graph, speed versus time. It's actually exactly the same graph. So I'm going to rewrite what we had before. I'm going to tell you that our change in position is our VIT plus 1/2 VF minus VI times T. So if you remember, we arrived at this thing around like the third or fourth step of the graph when we were deriving that last equation. Now this thing is delta V. And I just told you that acceleration is delta V over T. So let's rearrange. Delta V is equal to acceleration times time. So I'm going to take this chunk and plug it back into here. And I'm going to get change in position equals VI times T plus 1/2 AT times T. Well, T times T is just T squared. So change in position equals VIT, so your beginning speed times your time, plus 1/2 of your acceleration times time squared. Super important equation. You need that. Is that on our AP equation sheet? It is. It's right here. Now wait a minute. Those things don't look the same. What's going on? So what they did is they broke this out as your final position and your beginning position. If I bring this over to the other side, then that is x minus x0, which is change in position. Again, they don't call it VI, they're calling it V0. And this A has an X because they're trying to point out with all these X's that this thing is a scalar and that you're solving for the X direction. So it's a little annoying that the AP equation sheet doesn't match what you'll see in your textbook or what I usually write. You just have to get used to like translating the languages a little bit. Now, there's one last equation that I always write as VF squared equals VI squared plus 2AX, or 2A times change in position. And that is also in your equation sheet, but they'll say that it's just V squared because they don't use a final, equals v0 squared plus 2a times your change in position, x. Okay, so I'm not going to derive that right now. We're going to save that for a later unit, and I'm going to say, hey, remember there was an equation I never derived, and now I'll fill that out for you. So you get to use this equation sheet on the test. Keep it handy. You're going to need it. But there are some equations that you do not get. So here's a list of all the equations. All right. Oh, I can't squeeze it in there. Oh, here we go. So there's a list of variables. I'm going to copy them over. Delta position, your final speed, your initial speed, your acceleration, and your time. So there are 5 variables. Now, there are actually 5 equations that you need to hold on to. This equation, change in position equals speed times time, it's obvious they're not going to give it to you. And it is only true if you have a constant speed. If your speed is changing, then your position is not equal to your speed times your time. Because if your speed is changing, which speed times time? Is it your speed now or your speed 5 minutes ago? All right. You should always know that acceleration is equal to speed divided by time. But then I've given you basically 5 equations. And the reason I gave them to you is because there are 5 variables. And in each one of these equations, one of the variables is missing. Like if you notice here, VF equals VI plus A times T, there's no mention of position at all. You can't solve for it. You can't put a position in. So what we're going to say is that if you ever get a problem that has no position information, you're probably going to use this top equation. The second equation has no acceleration. So if the problem never mentions acceleration, you can use this to solve because you don't have to input it and you don't have to solve for it. And again, like this equation has no acceleration, this one has no final speed, this one has no time mentioned. So you can look through this list and say, oh, I can use this equation because it's also missing the information that I don't have. All right, hang on to these equations. Good luck solving.